Predicting how much can be made in chemical reactions is kind of like predicting how many items can be made at a factory. Suppose a manufacturer of bicycles has 4,815 wheels, 2,305 frames, and 2,255 handlebars. How many bicycles can be manufactured using these parts? This type of problem is a little different than the previous stoichiometry problems that we did because we're given 3 different numbers to work with instead of just 1. So in order to solve this problem, I need to know how many of each item is actually needed to build a bike. I know that I need 2 wheels in order to build 1 bike, so I'm going to take the number of wheels and divide it by 2, and that will tell me how many bikes I'm able to make using the wheels alone, or 2,407.5 bikes. I know that I need 1 frame for every 1 bike, so I could build 2,305 bikes with the amount of frames that I have. I also know that I need 1 set of handlebars for every 1 bike, and that will allow me to produce 2,255 bikes. Because the number of handlebars yields the smallest number of bikes, I'm only going to be able to make 2,255 bikes using those parts. Now I can also figure out how many parts of each kind are going to be left over. Knowing that I'm going to use all of the handlebars, I will have 0 handlebars left over. If I started with 2,305 frames and I use 2,255 of them, that's going to leave me with 50 frames left over. I can also do the same thing with the wheels. If I start off with 4,815 wheels and I know that I need 2 wheels per bike, I can take this 2,255 bikes and multiply it times 2 and know that I'm actually going to use 4,510 wheels. If I subtract those 2 numbers, I will have 305 wheels left over. So the part that ultimately limits the production of bicycles that I can make is the handlebars. And in chemistry, we would call those handlebars the limiting reactant. I like to abbreviate limiting reactant as LR. The limiting reactant is the reactant that runs out first and is completely used up during the chemical reaction. Just like in the bike example, the limiting reactant ultimately limits how much product can be made. And when I solve stoichiometry problems, the value of the limiting reactant will always be the starting value that I use to solve any stoichiometry problem. The other reactants are called the excess reactants. These are the reactants that are left over after the reaction is complete. So when I was building my bicycle, I used up all of the handlebars and I had some frames and some wheels left over. So the frames and the wheels could be considered excess reactants. When determining what the limiting reactant is in a chemical reaction, we have to know what the balanced chemical reaction is. Some rocket engines use a mixture of hydrazine and hydrogen peroxide as a propellant according to the chemical equation listed below. Hydrazine is N2H4, and then the hydrogen peroxide is H2O2. So which of those 2 reactants is the limiting reactant if I start off with 0.5 moles of hydrazine and 0.75 moles of hydrogen peroxide? The easiest way to determine what the limiting reactant is compare the amount of moles that I have with the amount of moles that I actually need in order for the reaction to occur. I'm going to begin solving this problem by writing the amounts that were given in the reaction underneath each reactant. So 0.5 moles of hydrazine and 0.75 moles of hydrogen peroxide. And then I'm going to label these as have because that's the amount of each reactant that I actually have. Now above my chemical formulas, I'm going to write need. And in order to determine the limiting reactant, I need to figure out how much of each reactant I actually need in order for the reaction to occur. And in order to do this, I need to look at the mole ratios. There is a 1 before the hydrazine, and there is a 2 before the hydrogen peroxide. So there's a 1:2 ratio between my 2 reactants, which means for every 1 mole of hydrazine, I need 2 moles of hydrogen peroxide. So I need twice as much hydrogen peroxide as I have hydrazine. So if I have 0.5 moles of hydrazine, I would need 1.00 moles of hydrogen peroxide. I can also determine the amount of hydrazine that I would need. For every 2 moles of hydrogen peroxide, I need 1 mole of hydrazine. In other words, I need half as much hydrazine as I have hydrogen peroxide. So if I have 0.75 moles of hydrogen peroxide, I need half of that amount, or 0.375 moles of hydrazine. Now all I need to do is compare how much I have to how much I need. I have 0.5 moles of hydrazine, and I need 0.375. So I have more than I need, and I will probably have some hydrazine left over. On the other hand, I have 0.75 moles of hydrogen peroxide, but I need 1 mole of hydrogen peroxide, which means I don't have enough hydrogen peroxide in order for the reaction to occur. Because I need more than I have, the hydrogen peroxide is going to run out first, and that makes the hydrogen peroxide my limiting reactant. Because I have extra of the hydrazine is my excess reactant, or ER. Now when I take each of these amounts of hydrazine and hydrogen peroxide and I react them, how much of each product is going to be made and how much of the excess reactant is going to remain unchanged? Well, I've already determined that hydrazine is my excess reactant and hydrogen peroxide is my limiting reactant. So again, before the reaction occurs, I had 0.500 moles of hydrazine and 0.750 moles of hydrogen peroxide. And I'm going to label this with a B for before. Before the reaction occurs, I have half a mole of hydrazine and 3/4 of a mole of hydrogen peroxide. I also have technically no nitrogen and no water before the reaction occurs. Now there's going to be a change in moles during my reaction, and I can use the symbol delta to represent the change that's going to occur. Because hydrogen peroxide is my limiting reactant, it is going to control how much of each product I'm able to make. It's also the reactant that's going to get completely used up. So I'm going to use up all of the 0.75 moles of hydrogen peroxide, leaving me with 0 moles of hydrogen peroxide after the reaction. So I'm going to label this row with an A for after. The amount of nitrogen that can be made can be determined using the limiting reactant. There's a 1 before the nitrogen, and there's a 2 before the hydrogen peroxide. So for every 2 moles of hydrogen peroxide, I will make 1 mole of nitrogen, which is half as much. So I'm actually going to make 0.375 moles of nitrogen. So afterwards, I'll have 0.375 moles of nitrogen that is produced. If I look at the mole ratio of hydrogen peroxide compared to water, it is a 2 to 4 ratio. So for every 2 moles of hydrogen peroxide, I can make 4 moles of water, which is twice as much. So if I have 0.75 moles, I can actually produce 1.5 moles of water. So after the reaction, I will have 1.5 moles of water that I've made. So these two answers in my bottom row, 0.375 moles and 1.5 moles, is the amount of each product that I can make. The second part of this problem asks how much of the excess reactant remains unchanged. Again, I need to go back and look at my mole ratios. Remember from the previous slide that for every 2 moles of hydrogen peroxide, I need 1 mole of hydrazine, which is half as much. So I can take this 0.75 moles and divide it in half, and I'm going to use 0.375 moles of hydrogen peroxide. Because I use 0.375, that means after the reaction, I will have 0.125 moles of hydrazine remaining. And so this is the amount of hydrazine that is in excess. Determining limiting reactants is something that requires a lot of practice, but once you get the hang of it, it's very easy. So we will work through several different practice problems just like this in class. The last thing that becomes important when solving stoichiometry problems is determining the percent yield. The percentage yield is the actual yield divided by the theoretical yield times 100. The actual yield is the amount of product that is actually made. And so when you're conducting the experiment in a lab, this is the amount of product that you actually make in the lab, and it would be what you would measure on a scale at the conclusion of the lab. Sometimes this is also called the experimental yield, because it's the amount that you make during the experiment. The theoretical yield is the amount of product that should be made by the limiting reactant. This value is always calculated using stoichiometry and is sometimes known as the accepted yield. Here's an example of how to calculate percent yield in a chemical reaction. Methanol can be produced through a reaction of carbon monoxide with hydrogen in the presence of a catalyst. The balanced chemical equation has 1 carbon monoxide and 2 hydrogens reacting to form 1 methanol. If 75 grams of carbon monoxide reacts to produce 68.4 grams of methanol, what is the percentage yield of methanol? In order to calculate percentage yield, we need the actual amount divided by the theoretical amount, and then that number multiplied times 100. Well, we know the actual amount because the problem gives us the actual amount as 68.4 grams of methanol, but we don't know the theoretical amount. Remember that the theoretical yield is always determined using stoichiometry, so we'll need to do a stoichiometry problem first before we can solve this problem. So I'm going to pull the 75 grams of carbon monoxide out because that's how much I know I'm starting with, and let's figure out how many grams of methanol I could theoretically produce. Remember, when doing a stoichiometry problem, this will need to get converted into moles first, and then we can go over to moles of methanol, and then we can solve for grams. So I'll begin by writing 75 grams of carbon monoxide, convert that to moles of carbon monoxide, convert that to moles of methanol, and then finally grams of methanol. On the bottom, I'll have grams of carbon monoxide so that cancels out, moles of carbon monoxide, and then moles of methanol. And now I can plug in my numbers. The molar mass of carbon monoxide is 28 grams per mole. According to my balanced chemical reaction, there's a 1-to-1 ratio, and the molar mass of methanol is 32 grams per mole. After multiplying all the way across my t-chart, I get a theoretical yield equal to 85.76 grams that I could theoretically produce. And so now that I know the theoretical yield and the actual yield, I can plug those values into my equation. So according to the problem, my actual yield is 68.4. According to the stoichiometry that I just did, the theoretical yield is 85.76. I take these two numbers, divide them, and then multiply times 100, and I get an answer of 79.8%. And that is the percentage yield of that particular reaction.